Today we want to discuss terminal velocity. We want to look at the derivation of terminal velocity of a solid sphere dropped in a viscous fluid. The problem we want to consider, considering a metallic sphere of radius A and density ρ, fall under gravity in a liquid of density this, that we are required to sketch the forces acting on the sphere, and hence also to show that the terminal velocity is given by the expression terminal velocity is equal to 2a squared in the bracket of the density of the solid minus the density of the fluid, all into gravity, all over 9 multiplied the coefficient of viscosity. For a body that is dropped in a viscous fluid, if we have a body, there are 3 forces acting on the body. One of them is the weight that is acting vertically downward, the viscous force, which is the drag force acting upward, and the buoyant force, which is the upthrust acting upward. These are the 3 forces acting on a body that is dropped on a fluid. Experimentally, the drag force is given by 6 pi, the coefficient of viscosity, the radius, then the terminal velocity. And we have told that the radius of that solid is given as a. So this is a, where this is the terminal velocity. The buoyant force, which is the density, upthrust, is equal to the density of the fluid, the volume of the object, and gravity. The weight of the object is mass times gravity, and mass is equal to density times volume. So we have the density of the object, the volume, and gravity. If we bring this together, for that body to be in a state of equilibrium, the weight must balance up. The weight which is acting downward must balance up with the 2 forces acting upward. So we have this expression. And when we bring the value for the weight, we have this. And when we bring the value for the viscous or the drag force, we got this. And this is the value for the the upthrust, which is the density of the solid, the density of the liquid, the volume, and gravity. But we know also that the volume of the liquid, we know that the value for volume is equal to 4 over 3 pi r squared. Now, since the body, the area, the radius is given to us as a, so this is going to be a cube. The volume is given as that. When we substitute the value for volume, we got this, and this. Now we want to make the terminal velocity the subject formula, because this is what we need. We are to make Vt the subject formula in that expression. And when we substitute all the value, this is the volume of the solid, and we substitute here, we bring this other way, and we got this. Making Vt the subject formula in the expression, we have 6 pi nu a Vt is equal to, we got this, that is making this the subject formula. Not really. We got this from here. When we make this the subject formula, we are having here, we divide through by this. When we divide through by 6 pi this, then that will give us the terminal velocity of this. So the whole of this is not there. When we make this the subject formula, we got this. And at the end of the day, the expression 4 over 3 divided by 6. If we divide by 6, we are going to have 4 over 3 times 1 over 6. And when we reduce this gives us 2, and this is 3, and that gives us 2 over 9. That is how we got 2a squared, all in the bracket of the density of the solid minus the density of the fluid, all into gravity, all over 9. Then we have the coefficient of viscosity. This is what we are to prove at, and this is the solution to the problem which we have. So the terminal velocity for an object of radius a dropped in a fluid is given by this expression. Thank you.